Let us discuss the application of Schrodinger equation in solving harmonic oscillator. We know harmonic motion occurs when system of some kind vibrate about equilibrium position. There are a lot of examples: thermal vibration of the atoms in lattice, motion of simple pendulum under the action of gravity. In simple case of harmonic motion, the restoring force on the particle of mass m is linear with the displacement. This means the restoring force is directly proportional to displacement of the particle from mean position. Therefore, we write F is equal to minus kx, and this is the well-known Fock's law. Now we use the Newton's second law of motion. We write this minus kx is equal to m into d2x by dy square, or we write in this fashion, which is equal to 0, and this is the second order differential equation of simple harmonic motion and has the solution of the type x is equal to a cos twice pi nu t plus phi, where a is the amplitude and phi is a phase constant which depends upon the value of x at time t is equal to 0, where nu is the frequency of vibration, and this frequency is given by this v nu is equal to 1 by twice pi into under root k by m. In both classical and modern physics, for small displacement x, restoring force reduces to Fock's law. Then small displacement can be expressed in terms of the Maclaurin series. It's f of x is equal to f at x is equal to 0 plus df by dx at x is equal to 0 into x plus half d2f by dx square at x is equal to 0 into x square, and so on. At equilibrium position, x is equal to 0, that is f is equal to 0, and x square and higher terms of higher powers of x are neglected since x is very small. Therefore, we write the Fock's law in this fashion, where df by dx is negative. Therefore, we conclude that all vibrations are simple harmonic for small amplitudes. Now the potential energy V of x is a function of x and can be obtained from Fock's law in terms of work done by particle moving from x is equal to 0 to x against the restoring force as follows. So V of x is equal to minus integration from 0 to x into this work done. Now putting the value of f of x, we get this is k into integration from 0 to x into dx is equal to half kx square. This equation is plotted as shown in figure. The particle will vibrate from minus a to plus a is the mean position, and this is the potential energy curve. It's potential variation of potential energy. The total energy E is related to amplitude by this equation. E is equal to half k square, where k is the A is the maximum displacement. Now we solve. This is the potential energy. Now we solve the Schrodinger equation for the oscillator under interaction of potential energy is equal to half kx square. So we write the Schrodinger equation d2 psi by dx square plus 2m by h cross square into E minus half kx square into psi is equal to 0. We rearrange this equation sorry, go back, we correct it. We correct this equation, that is this factor is correct. So we get, rearranging this equation, that is you multiply this factor, also we get this, okay, this we get this. Now rearranging we get now, that is d2 psi plus dx square under root k by m. Take k by m by h cross is taken common, so we get this type of equation. Then you divide this equation throughout by this factor, so we get h cross upon under root km into d2 psi by dx square plus 2e upon h cross square under root m by k minus 1 by h cross into under root km into x square into psi is equal to 0. We substitute the undetermined quantities such as y square is equal to this much, this, or y is equal to this root of this bracket into x, and alpha is equal to, you put this is equal to alpha, and we know that is nu is equal to 1 by twice pi into this under root k by m. So k by m, under root k by m is equal to twice by nu, or under root m by k is equal to twice by nu. So you put in this value of under root m by k, you get, that is alpha is equal to 2 into 2e divided by h nu. These two equations, 7 items. Now we know that is, we write in this fashion of d psi by dx is equal to d psi by dy into dy by dx, and second differentiation of this, d2 psi by dx square is equal to d2 psi by dy square into dy by dx into dy by dx, that means dy by dx square. So we put the value of dy by dx, that is this value, put here, put this value. So now we write h cross under root km, this goes to this side, d2 psi by dx square is equal to d2 psi by dy square. Now putting this in this equation, we get d2 psi by dy square plus alpha minus y square into psi is equal to 0. This is equation 10. To find the solution of equation 10, that is, we find asymptotic form of psi, that is, psi tends to 0 when y tends to infinity, because y is very large. Let us write equation 10 as in this fashion, or you write in this fashion, or this is equal to this. As y tends to infinity, y square is very greater than alpha, then alpha is neglected and we get this limit y tends to infinity, d2 psi by dy square by y square into psi is equal to 1. As the function that satisfies equation 11, this equation equation, then this function is of the form psi is equal to e raised to minus y square upon 2. So you find d psi by dy, we get minus y into e raised to minus y square upon 2. It is differentiation of this is, it is this factor, and differentiation of this function is minus 2y upon 2, that is minus y. So again differentiate this equation, you get d2 psi by dy square is equal to 2y square upon 2 e raised to minus y square upon 2 minus e raised to minus y square upon 2. Now to find this limit y tends to infinity is equal to this y square e raised to minus y square upon 2 minus e raised to minus y square upon 2, or you take common this, we get y square into e raised to minus y square by 2, because y square is very greater than 1. Equation 13 is, this equation 13 is the required asymptotic form of psi. Hence we write the asymptotic form of psi, that is psi is equal to f of y e raised to minus y square by 2, this equation. Differentiate this equation with respect to y, we get this. Now again differentiate, you get this total, or you write this, that is this factor 1, this 2 is minus 2y df by dy into e raised to minus y square by 2. Now this is the dou 2f by dou y square into e raised to minus y square by 2, and this is this y square, you take common, this is f of y into e raised to minus y square. So we correct here also, sorry, we correct this and show this equation. Let us show this. So now this, we get this equation. So substituting equation 14 and 15 in equation 10 behind, you get this equation, or this you take this, take common, goes to 0 to this side, this, or divide e raised to minus y square by 2 throughout, and then you combine these two terms, you get this is d2f by dy square minus 2y df by dy plus alpha minus 1 into f of y is equal to 0. This obey differential, this obey the differential form in f. To solve this equation 16, we expand f of y in power series in y. Hence we write this power series, f of y in terms of power series, or this is equal to summation n is equal to 0 to infinity a n y n. This is the equation 17. Now find df by dy in this fashion, or y into df by dy, you get this, or we write this summation n is equal to 1 to infinity a n into y raised to n. You again find d2 f by dy square from this equation. So this becomes 0, differentiation of constant, and you get direct 1 into 2 into A2, but differentiation of y with respect to y is 1. Then differentiation of this term, that is you get 2 into 3 into A3 into y. This is differentiation of y is equal to 2y. And this term, that is you get 3 into 4 into A4 y cube. You write this equation in this fashion, that is this n, and this n minus 1 into this an y raised to n minus 2. So this y raised to n minus 2 here, and this is, and n minus 2 is 1. So we get same equation. This equation can be written in this fashion, that is n is equal to, you put this n is equal to n plus 2 here. So n plus 2, n is equal to, you get n plus 1. So you put n is equal to n plus 2. You get this equation. Substituting equation 17, 18 and 19 in equation 14, you get this. You put solid, you should get this equation. Now in order to satisfy this equation for all values of y, the quantities in the bracket should be equal to 0. Therefore we put this is equal to 0. We rearrange in this fashion, or we get the final equation. This equation is called the recursion formula. And this formula enables us to find the coefficient A1, A2, A3 and so on. Now we discuss the energy levels of harmonic oscillators. If the series representing the f of y terminates for certain values of n, so all coefficients n are not to be 0. For all higher values of n, then psi tends to 0 as y tends to infinity, since this psi is equal to this f of y into this factor, because y goes to infinity, this goes to 0. This is possible only when this factor should be equal to 0, then we get psi is equal to 0. So this is equal to 0, so alpha is equal to, this goes to this side, 2n plus 1, and we know that is alpha is equal to 2 e upon h nu. So this is equal to 2n plus 1, or e is equal to, this h nu goes there, 2 divided by 2 to get cancelled, plus 1 by 2. So n plus half into h nu. These are the energy levels. This gives the energy of harmonic oscillator, and this varies with the value of n. This shows that for n is equal to 0, the ground state of oscillator possesses the energy E0 is equal to half h. This energy is called the 0 point energy, which is not possible to explain classically. The energy levels of oscillator was shown in figure. This figure you show this. This is the 0 point energy. This is E1 is equal to 3 by 2 h nu, 5 by 2 h nu, 7 by 2 h nu, and so 9 by 2 h nu, and so on. This energy is discrete energy level diagram of the harmonic oscillator. Thank you very much.